Howdy everyone. Today I'm presenting the SIGGRAPH 2025 paper Curl Quantization for Automatic Placement of Knit Singularities by Mitra and his colleagues from Boston University and Lightspeed, which solves a critical automation problem in computational knitting. That is, to determine where to place the irregularities needed to turn 3D shapes to machine knittable fabrics. Before we dive into more technical details, here's a quick introduction to computational knitting. It is an additive manufacturing technique that creates objects by interlocking yarn loops. Presumably, this is most commonly adopted in garment products, but it is actually used in applications beyond just clothing. For example, soft robotics with embedded sensors and actuators, wearable devices with integrated electronics, etc. Currently, designing knittable structures requires experienced knitting engineers who manually translate designs into machine instructions. This is labor-intensive and limits automation. Previous works have attempted both local greedy algorithms and global parameterization approaches, but both have their limitations. If the authors proposed a solution that's fast, automatic, and flexible. This is based upon their prior works that formulate knit planning as a stripe pattern optimization problem. I'm not going to get into details of these works, but for better interpretation, a high-level review is required. Basically, to generate a knit graph for a sock model, for example, we need to compose two orthogonal stripe patterns from mixed integer solves. Looking at this graph, on the left is a naive boundary-aligned coarse stripes that contain helices, which are highlighted in green. This helix persists in the knit graph, which is regarded unknittable. To solve this problem, the authors introduced a helix elimination constraint along the blue cycle, visualized by SIGGRAPH on the right. After solving subject to this constraint, their coarse stripes are completely helix-free. With the basic ideas explained, we can move to the core challenge that authors want to figure out: singularities. There are mainly three types of singularities, all illustrated in the corresponding text colors. The short row ends in the coarse direction. In pink is the partial rows that create local shaping. Increases in the whale direction in green means adding loops to expand the fabric, and decreases in the whale direction in orange is used to merge loops to narrow the fabric. Our goal is to place these singularities to make flat knit fabric conform to the curved surfaces. To achieve this goal, let's start with a knitting time function h that goes from 0 at the start to 1 at the end, illustrated by the graph on right. Here's a key geometric insight from this paper. The isolines of function h suggest where knit rows should go. As a result, it is intuitive to consider the gradient of h as a solution. Nevertheless, if we use gradient h directly, the spacing between isolines varies wildly. Consequently, we should normalize it for even spacing. Now we got evenly spaced strips, or namely rotated isolines in both directions, but here's another catch. Gradient h is not always integrable as it has curls. Visually, it looks like this in vector field and strips respectively. Although it sounds like an issue, the counterintuitive insight is that regions of high curl are exactly where we need singularities. For coarse or rows, curl of gradient indicates short row locations. For whale or columns, curl of rotated gradient h indicates increase or decrease locations. The intuition behind this insight is that curl measures how much the normalized field rotates. This is analogous to how knitted fabrics are woven at a knot area. For better understanding, here's a figure that illustrates the meaning of curl signals. In the graph, the bent cylinders have highest curl at the spine area, as it is the place where bending is most extreme. Similarly, for the spheres, high curl at the poles are places where surface curves most. In other words, curl indicates where level set spacing changes quickly, such that inserting singularities allows for more even spacing. Now the problem is reformatted as approximating this continuous curl signal with discrete integers such that we can use curl of gradient He as a heuristic for placement. This can be achieved through quantization. Mathematically, the authors formulate this as finding a discrete one-form sigma on a length complex. This formulation requires quite a bit mathematical background, which I'm not getting into for the sake of time. But on a high level, we can just think of it as a stripe pattern. The goal is to minimize the difference between our stripes and the target field gradient H. This optimization problem can't be solved at once as it would be a mixed integer problem. Instead, we approach it iteratively by starting with no singularities, then inserting singularity at a point of max absolute curl by computing curl signal and correcting it through subtracting local impulse from existing singularities. Simultaneously, we mask out forbidden regions to satisfy constraints like helix-free strips. With highest curl location found, we place pairs of singularities along time function isolines with the highest curl range in course direction. For whales, we place a singularity on the edge with the highest absolute curl. This process is repeated until no further improvements. As we greedily check potential edge pair candidates, and there are only a finite number of edges, termination of this algorithm is guaranteed. Practically, it should converge in about 20 to 50 iterations. Lastly, the solved course and whale strips are intersected to generate a smooth knit graph suitable for both artifact-free yarn level rendering and machine knitting. To validate the method, the authors applied machine knitting and rendered yarn-based visualizations of prototypical models in the 3D and cut-and-sew settings. Here are some results. Here are the rest of them. Note that all of these were actually knitted on an industrial Shimaseki knitting machine. The fabricated results show even stitch sizes and smooth patterns. No machine failures, no manual fixing required. For rendering results, the authors compared with two state-of-art pipelines, AutoKnit and stitch meshing. AutoKnit shows visible irregular rows and columns observed in these choppy patterns. Stitch meshing has some surface artifacts and inconsistent orientation. On the contrary, their methods yield smooth, artifact-free, and visually plausible results. This is because global optimization produces coherent patterns. Edge-based singularities enable proper knit graph construction. There's also a quantitative comparison to the author's prior work, which uses mixed integer approach. We can say it shows enormous speeds up around all kinds of fabrics. For those computationally timed out garment, these methods can handle it in less than a minute. Furthermore, the method supports intuitive user control as well, which is not possible in previous works. By default, singularities placed at geometrically optimals, but users can mask out regions to keep areas clear for color work or texture patterns. In cut-and-sew designs, users can align columns to boundaries with simple linear constraints such that whale columns won't flow arbitrarily across panel seams. In conclusion, the authors proposed a Curl quantization formulation and iterative algorithm that greedily places singularities over knit graph while maintaining all manufacturing constraints for both artifact-free yarn-level rendering and machine knitting. Of course, it has some limitations like reliances on good time function and high-resolution meshes, or no symmetry awareness for symmetric shapes. But in general, this enables truly automated 3D shape to knitted object pipelines for industrial manufacturing, functional applications, and digital content creation. This is all of my presentation. Hope you enjoyed it. Thank you.